Behavior of bistable elements. The basic bistable element to be examined in this session consists of two identical cross-coupled inverter circuits as shown in figure. Here, the output voltage of inverter 1 is equal to the input voltage of inverter 2. That is, VO1 is equal to VI2, and the output voltage of inverter 2 is equal to the input voltage of inverter 1, that is VO2 is equal to VI1. In the order to investigate the static input-output behavior of both inverters, we start by plotting the voltage transfer characteristic of inverter 1 with respect to the VO1 minus VI1 axis pair. Notice that the input and output voltages of inverter 2 correspond to the output and input voltages of inverter 1 respectively. Consecutively, we can also plot the voltage transfer characteristic of inverter 2 using the same axis pair as shown in figure. As you can see, this is the figure about static behavior of the two inverter basic bistable element. A circuit schematic here. B intersecting voltage transfer curves of the two inverters showing the three possible operating points as you can see here. C qualitative view of the potential energy levels corresponding to the three operating points as you can see here. It can be seen that the two voltage transfer characteristics intersect at 3 points. Simple reasoning can help us to conclude that two of these operating points are stable, as indicated in figure. If the circuit is initially operating at one of these two stable points, it will preserve its state unless it is forced externally to change its operating point. Note that the gain of each inverter circuit, that is the slope of the respective voltage transfer curves, is smaller than unity at the two stable operating points. Thus, in order to change the state by moving the operating point from one stable point to another, a sufficiently large external voltage perturbation must be applied so that the voltage gain of the inverter loop becomes larger than unity. On the other hand, the voltage gains of both inverters are larger than unity at the third operating point. Consecutively, even if the circuit is biased at this point initially, a small voltage perturbation at the input of any of the inverters will be amplified, causing the operating point to move to one of the stable points. This leads to the conclusion that the third operating point is stable. The circuit has two stable operating points, hence it is called bistable. The bistable behavior of the cross-coupled inverter circuit can be visualized qualitatively by examining the total potential energy level at each of the three possible operating points. In the figure, it is seen that the potential energy is at its maximum at two of the three operating points. Since the voltage gains of both inverters are equal to 0. By contrast, the energy attains at a maximum at the operating point at which the voltage gains of both inverters are maximum. Thus, the circuit has two stable operating points corresponding to the two energy minima and one unstable operating point corresponding to the potential energy maximum. Figure shows the circuit diagram of CMOS 2 inverter bistable element. In the figure, a circuit diagram of bistable element, as you can see here. B, one possibility for the unexpected time domain behavior of the output voltages if the circuit is initially set at its unstable operating point, as you can see here. Note that the unstable operating point of this circuit in all four transistors are in saturation, resulting in maximum loop gain for the circuit. If the initial operating condition is set at this point, any small voltage perturbation will cause significant changes in the operating modes of the transistors. Thus, we expect the output voltages of the two inverters to diverge and eventually settle at VOH and VOL respectively, as illustrated in figure. The direction in which each output voltage diverges is determined by the initial perturbation polarity. In the following, we will examine the event more closely using a small signal analysis approach. Consider the bistable circuit shown in figure, which is initially operating at VO1 is equal to VO2 is equal to VTH, that is at the unstable operating point. For the analysis, we will assume that the input gate capacitance Cg of each inverter is much greater than its output drain capacitance Cd, that is Cg is greater than Cd. The small signal drain current supplied by each inverter 1 and 2 can be expressed in terms of the small signal gate voltage of the inverter as follows. Note that the drain current of each inverter is also equal to the gate current of the other inverter. Ig1 is equal to ID2 is equal to GM VG2. Ig2 is equal to VD1 is equal to GM VG1. As you can see in this figure, small signal input and output currents of the inverter. Here GM represents the small signal transconductance of the inverter. The gate voltages of both inverters can be expressed in terms of the gate charges Q1 and Q2. VG1 is equal to Q1 by Cg, VG2 equal to Q2 by Cg. Note that the small signal gate current of each inverter can be written as a function of the time derivative of its small signal gate voltage as follows. Ig1 is equal to Cg V dVg1 by dt. Ig2 equal to Cg dVg2 by dt. Combining the both equations, we obtain Gm Vg2 is equal to Cgv G1 by dt. Gm Vg1 equal to Cg Vg2 by dt. Expressing the gate voltages in terms of the gate charges, these two differential equations can be written as Gm by Cgq2 is equal to dq1 by dt. Gm by Cgq1 is equal to dq2 by dt. Both differential equations given in equations can be combined to yield a second order differential equation describing the time behavior of gate charge Q1. Gm by Cg Q1 equal to Cg Gm d power 2 Q1 by d power 2 gives d power 2 Q1 by d power 2 is equal to Gm by Cg whole square Q1. This equation can be expressed in more simplified form by using tau naught, the transit time constant. T power 2 Q1 by T square is equal to 1 by tau naught square Q1 with tau naught is equal to Cg by Gm. The time domain solution of equation for Q1 yields Q1 of t is equals to Q1 naught minus tau naught Q1 dash naught by 2 e power minus t by tau naught plus Q1 0 plus tau naught Q1 dash 0 by 2 e power plus t by tau naught. Here the initial condition is given as Q1 of 0 equal to Cg dot Vg1 0. Note that Vg1 is equal to V0 2 and Vg2 equal to V01, replacing the gate charge by both inverters with the corresponding output voltage variables. We obtain V02 of t is equal to 1 by 2 V02 of 0 minus tau naught V0 dash 2 of 0 e power minus t by tau naught plus 1 by 2 V02 of 0 plus tau naught V0 dash 2 of 0 e power plus tau plus t by tau naught V0 1 t is equal to 1 by 2 V0 1 of 0 minus tau naught V dash 01 of 0 e power minus t by tau naught plus 1 by 2 V0 1 of 0 plus tau V dash 01 of 0 e power plus t by tau naught. For large values of t, the time domain expressions of equations can be expressed as follows. V0 1 of t similar to 1 by 2 V0 1 of 0 plus tau naught v dash naught 1 of 0 e power plus t by tau naught. V naught 2 of t similar to 1 by 2 v naught 2 of 0 plus tau naught v dash v dash naught 2 of 0 e power plus t by tau naught. Note that the magnitude of both output voltages increase exponentially with time depending on the polarity of the initial small probations. T v naught dash d v naught 1 0 and d v naught 2 0. The output voltages of both inverters will diverge from their initial value of VTH to either VOL or VOH. In fact, the polarity of the output voltage perturbation dV01 must always be opposite to that of dV02 because of the charge conservation principle. Here the two opposite voltages always diverge into opposite directions as expected. The phase plane representation of this event illustrated in figure shows that the operating point V01 equal to VTH, V02 equal to VTH is unstable. The operating points V01 equal to VOL, V02 equal to VOH and V01 equal to VOH, V02 equal to VOL can be shown to be stable using small signal models at the corresponding operating points. V01 VTH, VOH or VOL, V02 VTH, VOL or VOH. In addition to the time domain analysis presented here, an interesting observation can be made for the two inverter bistable element. While the bistable circuit is settling from its unstable operating point into one of its stable operating points, we can envision a signal traveling the loop consisting of the two cascaded inverters several times. The time domain behavior of the output voltage V01 during, here you can see the figure phase plane representation of bistable circuit behavior. Here you can see the figure propagation of transistor signal in the two inverter loop during settling. His period is approximated as follows: V01 of t by V01 of 0 equal to e power plus t by t0. If during a time interval t the signal travels the loop n times, then this is equivalent to the same signal propagating along a cascaded inverter chain consisting of 2n inverters. Expressing the loop gain, combined voltage gain of two cascaded inverters with A, we obtain a power n equal to e power plus t by tau naught. This expression describes the time domain behavior of the diverging process until it reaches stable points as depicted in figure. Thank you.